So, in the 10th slide, I am going to just look at what I have not covered and then maybe take that. So, this is the key aspect of this. So, we want to create an architecture that does not impose the fixed length limit. All right. Okay. So, what do we require to build such a architecture? So, state, so far we have never spoken about the word state, right. So, now we are going to be talking about the state. States are very important. So, for you to really go to the next state, I need to know what happened in the previous state. So, without the knowledge about the previous one, I cannot move forward. Okay. So, states are extremely important in the RNN, also in the NLP as well, right. In order to use the previous state, we need to somehow store it, right. So, we need a storage mechanism where the states are stored. All right. So, this we already have spoken. So, we should be able to provide a sequential input, so that the model should be able to really take the sequential input of any length. All right. So, we also would see later that the RNNs do not just encode the similarities between words, but also between the pair of words. It also creates the similarity and also finds out the analogy. For example, if you give the word Chennai is Tamil is same as London and English, right. So, in this case go and went is same as run and ran. So, we should be able to find the analogies in the recurrent neural network as well. So, we will spend one half an hour or 45-minute session on how to really capture the analogies in the corpus. So, as I mentioned earlier, it is almost similar to what we have seen, but there is one small change that you will see here, right. This is the recurrent part. So, there is a small loop in the hidden layer part. So, this is your input layer, your hidden layer, this is your output layer, correct. So, we have introduced some small stage. So, why we have introduced it here? So, when you take the input and then create a linear combination and then store it as a hidden value, right. So, it really takes the essence of the input and the weight vectors that we have trained so far, okay, and that we want to maintain that. So, we capture that in the previous state and then include this as part of the new state. So, that means we are incorporating whatever we have learnt earlier in the embedding layer and then incorporate that as part of the current state. So, we will see how this could be done. So, this is one simple recurrent neural network where there is a small loop introduced in the hidden layer. So, this is going to give us the time series. Okay. So, this is going to give us the time series. Let us see how it does. So, in this slide we will see that the same neural network that I showed you earlier can be unrolled. That means, I have the state of the previous hidden layer and I connect to the state of the current hidden layer through another weight that I have created. Okay. So, now we are introducing one more parameter. So, earlier we had the embedding weights, we had the context weights. So, now we have one hidden layer to hidden layer, there is one more parameter. So, now if you want to learn, so we need to learn not only this, but also this, sorry, this should be 3. So, these 3 parameters should be learned. So, this really encodes what you have given as input and combine that with the weight vector, right. So, this is the linear combination of these two, and this is what is stored as the previous state as well. And then the state of the linear combination that we had gotten earlier is connected to the current state through the weights, which connects the previous timestamp of h and the current timestamp of h through the weights here. Got it. So, this is our memory part that we are talking about. We want to retain this, so that we keep knowing what has happened in the previous time slice, a time slice even before that and before that. So, from the start till the time equal to t, we will have to capture this and then maintain this in our memory, right. That means, it has managed to maintain the activation values of the time slice, activation values of h across the time slice that we are having. Okay. All right. So, the updation of weights are very similar to what we had seen. Only change that we have is this activation is calculated by combining these two and this. So, let me erase those so that it becomes clearer. So, this activation is computed using 1 and 2. Okay, so, this is what we have as 2 in this. Okay, so, and then the rest is same like we had seen. So, this activation based on the sigmoidal that you have used would be connected to the context weights, and then finally, you get an output layer. You apply softmax or hierarchical softmax depending on how you want to optimize your network, and then start doing the process of training and so on. So, when you do the training, we do not just have this. Let me again erase all those points. The back propagation is not only on these and these weights, it has to be propagated to these as well. So, this is little hard when compared to what we had seen earlier, and if you have multiple time slices, you will have more of this particular one. So, it will be repeated. So, you will have 1 and there is this is t plus 1, t plus 2 and so on. So, let us this is my box. So, every time okay. So, that means the back propagation, if suppose we have only about 3 of these, it start from here and then we go back and do it. So, every time when you come from the output layer, you have to update this, you have to update this based on y and v, you have to update this based on y, v, w and whatever you have earlier and so on. I am not going to be covering it in this session, I will take a separate session to see how training can be handled in the recurrent neural network part. Okay. So, it is just for the understanding of how the weights are calculated. So, we have ht is computed using the function, okay, and then yt is computed using v and ht, and where ht is your input and ht minus 1 is the state of hidden weights at time t minus 1, right. Okay. So, there are, so having understood how a recurrent neural net is constructed, right. When you look at the neural net, which is a simple one, you have lots of options here. Okay. Unlike in the previous case, we can build the neural network using several ways. For example, I can just create one to one. Okay. So, where I can use that neural net as a standard neural network for classification purpose, correct. And then I can have one input to many output. I can use it for image descriptions. So, I can keep feeding one word and then it can give me various options connected to that particular word. And then I can have many to one, basically used in the sentiment analysis, right. And then we have many to many, we can use it for machine translation. So, I am talking about this one. Okay. So, there is a encoding part and there is a decoding part. Okay. And then there is a many to many combined differently. So, we can use it for frame labeling of video sequences. Many people have used these network for various applications. I have just listed based on the usage of these architecture for various applications. Okay. And also you will see that there are some more complex networks that we can build. This is another way of creating architecture. So, there is enormous capability in terms of changing the architecture depending on what you really want to do with this RNN. Okay. So, this is just to give you an idea of how differently you can create recurrent neural networks. This is a very simple feed forward algorithm, as I discussed this earlier. So, I am going to skip this. Again you will see various representation of this. I just want to give you the various representation of the same recurrent neuron that appears in various papers, research papers and technical papers. Okay. So, this is one more representation of the same. Okay. So, again the representation of a simple recurrent neuron in a different format, it is same as what we saw earlier here, right.